This is part 4 of the first lecture of week 9, where we discuss the existence of the Laplace transform. There are functions for which the improper integral in the Laplace transform fails to converge for any value of s. For example, the function f of t is 1 over t is like this. It grows too fast near 0, so the integral diverges. Likewise, no Laplace transform exists for the function f of t e to the power t squared, which increases too rapidly as t approaches to infinity. Fortunately, the set of functions for which the Laplace transform exists are quite large, and the functions that usually arise in applications are included in this set. So we now discuss some properties which will guarantee the existence of the Laplace transform. The first that we need to define is jump discontinuity. A function f maybe on some interval ab is said to have a jump discontinuity at some point in this interval if f is not continuous or discontinuous at t0, but there exists limit t approach to t0 maybe from the right or the limit t approach to 0 from the left. And also definition of the following. So this is jump discontinuity and definition of piecewise continuous function. F is piecewise continuous on some finite interval, let's say AB, if f is continuous at every point of this interval except possibly the finite number of points, and in this finite number of points f may have only jump discontinuity. So continuous at every point of AB except for a finite number of points at which f has jump discontinuities. And f is piecewise continuous on the sub-interval 0 infinity if f is piecewise continuous on every interval from 0 to n, where n for all n positive numbers. So f is piecewise continuous on some finite interval if it's continuous at every point except just finite number of points at which f may only have just discontinuity. And f is piecewise continuous on semi-interval from 0 to infinity if f is piecewise continuous on each finite interval from 0 to n for every n So let's consider example of piecewise continuous function. So this is example 6. So f of t is, let's say, t when t between 0 and 1. Let's say this is 2 when t between 1 and 2. And let's say this is t minus 2 squared, t between 2 and 3 included. And the question is it piecewise continuous on segment from 0 to 3? And the answer is yes. F is piecewise continuous on 0, 3, since it is continuous at every point of 0 and 3, but points at which points this is discontinuous. At 0 it's even not defined, right? At 1 it's also not defined, and at 2. So between these points 0, 1 and 2 we have the functions linear function, which is continuous, the constant function 2, which is also continuous, quadratic function, which is also continuous. And between them at this point 0, 1 and 2 we have discontinuity, but we still have the limits, right? So let's sketch the graph and see what the function is. So from 0 to 1 this is just, so at 0 it's not defined, at 1 it's not defined. But here the left hand side limit exists, and here the right hand side limit exists. So we have just discontinuity at points 0 and 1. And between 1 and 2 we have function which is just 2. Again at the points 1 and 2 it's not defined, but the limits exist, right? And from 2 to 3 this is parabola. So at 2 this is defined, this is 0, and at 3 this is 1, and between them we have a parabola. So this is example of piecewise continuous function. So you see that the piecewise continuous function can be split into some subintervals on which the function is continuous, and between these intervals we may have some jumps. So here we have jump discontinuity, and here we have jump discontinuity. And now let's discuss another notion which we will need. So another definition: a function f is said to be of exponential order alpha, exponential order alpha, if there exist positive constants t and m such that the absolute value of f of t is less than or equal to m times e to the alpha t for all t larger than or equal to big T. So starting at some point, starting from this capital T, this function f of t, the absolute value of this function, becomes less than exponent for some exponent order alpha. This is in fact, if you remember, the big O estimate, right? f now is big O of exponent. So f doesn't grow faster than exponent e to the alpha t. For example, f of t is e to the 5t sine 2t, and since sine 2t is bounded function between 1 and 1, we can estimate this as e to the 5t, in fact, for all t, right? For all t. So this is function of exponent order 5, of exponential order 5. Another example is f of t is e to the t squared is not of exponential order alpha for any alpha. So there is no alpha such that this function can be estimated as m e to the alpha t. And how we can see this? In fact, if we think about this estimate, this is limit as t approaches to infinity of the ratio. So we can write the following: if limit t approaches to infinity f of t over e to the alpha t is m, some m, or 0, then f of t is of exponent order alpha. So you can check using this limit. And if you look at this function e to the power t squared, and if you look at the limit e to the power t squared over e to the alpha t, this is limit t approach to infinity e to the power t squared minus alpha t. And since alpha is fixed, so this approach to infinity. So the limit does not exist. So this is not of exponential order alpha. And now let's formulate the main theorem of the existence of the Laplace transform, theorem 2. So this is existence of Laplace transform. If f is piecewise continuous function on 0 infinity and of exponential order alpha, then the Laplace transform of f at a point S exists for all s larger than this alpha. So this theorem gives you precise criteria when the Laplace transform exists.